Okay, so we start off with what we're going to try to cover today, and this is the analysis of clinical trials. When we talk about analyzing clinical trial, one should think about, let me just remind everybody, also, with faculty, we've all decided that we will give you a PDF of all the presentations. You don't need to be taking pictures, etc., because then you just clutter your phone with pictures that you will never look at very carefully later. So we'll give you this. So don't worry. See, most of us don't have the slides prepared 2 weeks ago. Most of us have our slides prepared 10 minutes ago. So that's why you don't have it beforehand. And but afterwards, we will just provide them all to Vignesh as a PDF. He has all of your emails. He will get them all to you. So don't worry about that. Anyway, so more paying attention than trying to focus your phone. So when we talk about analyzing clinical trials, we have to keep in mind that the study is designed for exactly one analysis. We often fall into the trap of, I can have this study and I can analyze and get 50 papers out of it. I can have my students do this. I can have this and that. Yes, those are secondary things. But the study is designed to answer one research question. There is only one analysis of a clinical trial. You will find out that that is actually a boring, simple test that we do. So the analysis, and I put it in red, the analysis is just the primary analysis of the primary study outcome. Okay. And there we'll talk about CONSORT reporting guidelines for the primary analysis. But you have invested a lot of your career, or 2-3 years, into this study. You don't want to just do one analysis and one paper. You want to do multiple analysis. You have collected multiple outcomes. You have collected a lot of other information that is important and interesting, and you want to do secondary analysis. So there is only one primary analysis, but then there's multiple secondary analysis. And that's when the fun begins, with subgroup analysis, with looking at safety outcomes, looking at exploratory outcomes, looking at economic outcomes, and maybe other things that I have not included here. We'll talk about statistical considerations and the misuse or abuse of p-values. We'll talk about two types of analysis. The first lecture is going to be the analysis at the end of the study. But we will see that ethics dictates that if a study is going to last a long time, that's why that T of Picot is important. If the study is going to be a long duration study, either from first patient enrolled to last patient completing follow-up, if that period is long, then you are forced by ethics to look at the data in the interim. Why? Because you may find that you've already answered the question in the interim. If you've answered the question already because there was strong evidence that one is that more efficacious than the other one, or it's not inferior, then you should stop the study and report the results, not only for benefiting the people in your control arm in the study, but also people that have that condition that are outside your study. So we'll talk about the ethics dictating that we do interim analysis. Ethics will dictate it, and that brings a complication because now we're testing the same hypothesis multiple times in the study, not once at the end. So statisticians had to deal with repeated analysis of the same question with accumulating data. And it was not an easy thing to do. And it was done in the 1970s, basically. We'll talk about that when we talk about the interim analysis. So that'll be a separate lecture. But then we'll have analysis of complex designs. And I think Professor Jayasila will talk about the crossover analysis, or I don't know if Vishal is going to do that one. And then cluster designs, we'll talk a little bit about that. We have more on analysis of clusters and the whole issue of cluster studies on Friday. Okay. All right. So let's get started. So what we mean by analysis of a clinical trial is answer the primary hypothesis, which is this intervention related to this outcome. And we have this intention to treat principle. The intention to treat principle comes from basically the notion that in real life, even though we're doing this as a very artificial experiment, we want to have some things that are like real life. What happens in real life? You are have a patient that comes to you, you diagnose their problem, and you prescribe a regimen to deal with that problem. But you prescribe it. You recommend this. You should get this medication. You should exercise more. You should change your diet. You should do this. You should do that. And what do people do? Whatever they want. Some of them follow the instructions. Some of them don't follow the instructions. Some of them follow them partially. Some of them get tired. Some of them feel better, so they stop. Some of them feel worse, so they stop. All of these things happen. And you intended to treat them with that regimen you prescribed. So the same thing we're going to do here. By randomizing them to a regimen, we are intending for them to follow that regimen. Some of them will not, some of them will, but that's reality. So we are forced to, in the primary analysis, to not take into account, oh, this person didn't even take the medication. No. Some people will not take the medication in real life also. So we are forced to do it. So anybody that's randomized has to be included in the analysis. There is no choice. You cannot argue, no, this person actually did not, whatever. So we'll talk about that. People try to not do intention to treat, but you are forced to do intention to treat. So the lemma is, if randomized, analyze. Okay, that's why you have to be very careful. You don't like some places they randomize and they still, to be eligible, they needed some laboratory test, and the laboratory takes 24 hours or takes 48 hours. But no, the patient is here, let me randomize him. Then the laboratory comes back and says, no, he's not eligible, but you randomized him. Now you have an ineligible person randomized, but you still have to analyze him. You cannot drop him out. All right. So the primary analysis outcome variable is the one that is, we talked about the outcomes, should be the clinically relevant event or endpoint that then we talked about yesterday, that it is a random variable. So a clinical event is not the outcome. And I give the example here of the MI and possible outcome variables for that clinical event can be the occurrence of it, or can be the number of occurrences, or it can be time to the first occurrence of the event, times to the occurrences of the multiple occurrences of the event, right? Recurrent event analysis. Now, the primary outcome also is the one that you've chosen very carefully in your exercise. It's the one that you're going to use to judge the treatment effectiveness. It's the one that the study is designed on. It's the one that the sample size is based on. That's what's very important, right? Now you have these multiple secondary efficacy ones. You have multiple secondary safety ones. You have process ones. People want to know screening is a process, and detecting cervical cancer is an endpoint. But you could choose a process one to be your primary one. There's nothing wrong with it, but you have to, you've chosen it carefully. You have economic outcomes. Most times, most trials don't have economic outcomes as their primary one, but they could, right? Sometimes in many of your studies, you're looking at, I'm going to measure that neurodevelopment index, BSID-4, at 6 months, 12 months, 24 months. And they specified the outcome is at 24 months. So the outcome could have been at 6 months, could have been at 12 months, but they have to specify at which time point you have, because it's only one outcome, not 3 outcomes, right? So you have to say that, but you may be interested in analyzing what happened at 6 months, what happened at 12 months. That would be a secondary analysis, not the primary analysis. We also will have multiple looks at accumulating data, and we'll talk about that after in the second lecture after this. And then you have multiple analyses that you could do. You may have a composite outcome, but now you're interested in studying each component of that composite outcome. And so you may want to do that. You may also have surrogate outcomes, like, the detection of cervical cancer is only possible if you're screened. So screening is a precursor, not a surrogate. It's a precursor. But surrogate outcomes are ones that, if they occur, then the definitive outcome is very likely to occur too. And it may be one that occurs earlier. It's maybe easier or cheaper to measure than or observe than the primary outcome. So sometimes you have multiple surrogate outcomes that you want to study as well. And we've been talking about, you may have residual confounding, especially when we do small samples, clinical trials, that things are not balanced out. And so therefore we need to adjust for them. Again, those become secondary analysis. The primary outcome is primary outcome analysis is crude, unadjusted. And then you have the subgroup analysis and multiple sensitivity analysis, because we had missing data on some of these things. So we did not have it on these people. What if they had done this? What if they had done that? Should I impute data? We'll talk about that. Usually imputing the outcome is seen as a bad thing to do. People don't trust results if you have to impute your outcome. We'll talk about, that's why we look at time to event analysis, so that we don't have missing data or the outcome variable. Okay. So when we have this intention to treat principle, the implications is that the analysis of the primary outcome is crude and simple. Crude means unadjusted. You don't adjust for anything. People that did not take it, people that had good adherence, bad adherence, people that actually missed some visits, or people that did not follow the protocol correctly in one respect or another. It's simple, it's unadjusted. It only depends on the type of outcome you have. Is it a continuous outcome? Is it a binary outcome? Is it a time to event outcome? Depends also on your study design. Is my study design a crossover? Is my study design factorial? Is my study design 3-arm parallel, or whatever it is? And it also depends on whether it's your hypothesis is a superiority or a non-inferiority. So those things are, but not the aspects of the conduct of the trial. So if the result of your analysis is negative, then what you do is you say, well, did I have adequate power for detecting anything in this effect? So I look at how much power I had, and I rule out poor quality. Maybe it was due to poor quality of the study. If I get a positive result, I still need to check, did I get it because there was some bias on this? Don't celebrate immediately because you got a significant result without checking if there was due to some bias that you got this to happen. So we have biases that come by the way you designed it, and hopefully that does not occur, or how you conduct it. Maybe it was so poorly done that people in the control arm did not follow things and they did not get results there. So you got a bigger effect than you expected because they got no effect in the control arm, and you got a really normal effect as expected in the intervention arm. So now you got a really big effect. And so you got, because of that bias, you got a significant result. So you have to sort of check these sorts of things. And then you may have this residual confounding or differences in groups due to post-randomization choices. So people say, once I get significant result, I'm happy, and that's it. No, you still need to check that that significant result was not due to some bias in how you did the study or how you did the analysis as well, and so forth. Okay, so what are the statistical considerations in the analysis of the primary outcome? The types of variables. We have two types of variables that we collect before randomization. We call those baseline variables. Things like their age at the study entry, the severity of their condition, age, sex, anything else, BMI, whatever. We call them fixed covariates. Fixed in the sense that they're not changing over time. Well, yes, their age is changing over time. Their BMI is changing over time, but the BMI measured at baseline is not changing over time. And their age at baseline is not changing over time. That's why we call them fixed. Their systolic blood pressure measured at baseline is that one value that's not changing over time. Their systolic blood pressure, if you measure it during the study, that's changing over time. But at baseline, there's only one, and that one is fixed. And why do we have those? Those are to check eligibility, and we will use them to see if randomization balance things, and it will permit us to do subgroup analysis. But most of the things we're interested in are post-randomization. We call those follow-up variables. And these are ones that change over time. So we call them time-variant covariates. And so that the neurodevelopment score is changing over time. We only measure it at 6, 12, and 24 months, but it's changing. If we're interested in their in an HIV study, we may be interested in their CD4 count. Well, that CD4 count is changing over time. And we only measure it at some particular time points, but then we'll have it at multiple time points. So you have to decide what is important in your study to be measured over time. You have to decide what is important in your study to measure at baseline. And so when you're designing your protocol, you always have to say, these are the things that we're going to collect, that you'll have to have your case report form, etc. We'll have those. But you also have to say, during follow-up, we are going to be collecting this, this, or that. What typical things we collect, in addition to clinical and variables that talk about the condition of the patient, we also have process variables, like, are they adherent to the protocol? Are they taking the pills? Are they putting the eye drops in? Are they eating the way they're supposed to, or whatever? So we have process follow-up variables. We also may know, it may be important that they come to clinic visits on a regular basis because advice is being given, things are being measured on them, things are being given, not only advice, but they're given part of the intervention is updated, they're given more or changing their dose or whatever. So we need to monitor participant care and monitor adverse events. So adverse events are collected not only when they come to clinic visits, we also, for ethical reasons, we have usually allow them to report and call in any problems that they have. So we have dedicated nursing staff or patient care staff that are there with a hotline or a WhatsApp number that any participant can just say, I'm having this today. I woke up with a headache. Was this related to the intervention or something like that? So these sorts of things you want to look at. But the primary outcome variable is the analysis of the trial. And we have all the other outcome variables that we may collect. So what are the types of outcome variables? What are the measures of effect and analysis methods? So if it's a continuous one, so I'm looking at a score, I'm looking at an index, I'm looking at a measurement of something on a continuous scale, I can look at it as the mean value at a given time point, or the median value at a given time point, or the 95th percentile at a given time point, or whatever characteristic I am designed my study for and powered for at a given time point. But most people also like to look at changes from baseline. The neurodevelopment score, you don't have that at baseline. It's something that's measured as the child changes. So you only have the mean value of it at 24 months in one arm and compared to the mean value in the other, or the median in this arm compared to the median in the other. But you could have change in weight in a study. If weight was in the obesity study, suppose they were looking at weight, you could have their change in weight, or they could have their weight at a given time point. And people want to say, sometimes I want to study change, and sometimes I want to study the actual weight of it. Which is the clinically important metric? It's up to you to decide. But you want to maybe adjust for the baseline weight and see that change, is it affected by their baseline weight where they started? So we talk about differences and differences as a metric, usually in continuous ones. How do we test it? Very simple. T-test. The same thing you had in your first course on statistics. If your data, if you have a small study and your measure of this, let's say the neurodevelopment score doesn't behave like a bell-shaped distribution, and you have a small sample, then you could use the Mann-Whitney test or Wilcoxon rank sum, for example. But it's a simple test, nothing out of the ordinary. If your data are categorical, your outcome is level of pain, for example, then you would have none, mild, moderate, severe. It's a categorical ordinal one. So you look at what is the frequency distribution, what is the percent of people that are none, mild, moderate, severe in intervention, what are none, mild, moderate, severe in control. And you compare those two distributions. How do you do it? With the chi-squared statistic. And which test do you use? Fisher's exact test. Many people don't realize that Fisher's exact test uses that chi-squared statistic. It just calculates the p-value for the chi-squared statistic exactly, while the chi-squared test uses the same statistic, but calculates it approximately. So usually I prefer the Fisher's exact test unless my software is not good enough and it won't handle that size, and then I will use the chi-squared test. Now, most of the time, we don't have ordinal scale as the outcome. We usually have binary. Remember, we talked about most physicians like binary outcomes. And so we'll have binary dichotomous outcomes. Now we have proportions, and we handle them whichever way we like to handle them. We can look at just the proportions at a given time point. We can calculate relative risk, taking the ratio of the proportions, or we could take the risk difference, taking the difference of the proportions, or we can take 1 over the risk difference, and that's the number needed to treat. It doesn't matter how you like to interpret it, because the test is exactly the same. The significance will be exactly the same. Most of us statisticians prefer risk difference, but Most physicians that I know prefer ratios, so they like relative risk. What is a test that we use? We do Fisher's exact test or chi-square test. Or we could do a simple logistic regression, for example, here as well. It'll give you exactly the same result if you do it with not adjusted for anything, okay? So very simple test, the primary analysis, nothing complicated. If I have survival outcome, so it's time to the occurrence of the event, time to the occurrence of that composite, time to the occurrence of screening, for example, you could look at not whether they get screened or not, but do people get screened earlier in one arm than the other, for example. So now your outcome is not the occurrence of screening, but it's time to the occurrence of screening. If you had that, you have a time to event outcome variable, and time to event outcome variable is called survival one. And just why is it called survival is a very interesting thing. After the Industrial Revolution, at the turn of the 19th century into the 20th century, all this manufacturing was taking place. You know, Henry Ford was making cars. People were making all sorts of device toasters. They're making refrigerators. They're making all sorts of things. And people were interested, how long does this thing last before it fails? Should I buy this toaster or buy that other toaster? Which one is going to fail early? Should I buy this light bulb or that light bulb? And what people were observing is, how do I know my company is selling light bulbs and I want to sell my light bulbs? So what should I do? I have to advertise, oh, this light bulb will last so many hours. Okay. So what I did as a owner of a light bulb company is I would take a sample of 1,000 light bulbs or 100 light bulbs, however many I want to sacrifice because they're costly. And I look at the hours until they fail, right? So I take time here. And at the beginning of time, let's say I have 1,000 light bulbs, all of them, the probability of being good is 1 because all of them are still working. I put them in a grid, I tighten them, I give them electricity, and I watch. And I have somebody sit around and watch, and then all of a sudden, one fails. And a lot of them fail, and another one fails. Eventually, after 800 hours or 300 hours, I don't know how many hours, let's say 800, all of them have failed. So now I'm down to 0 that have not failed. At the beginning, 100% or the probability of failing is, of not failing is 1, of surviving is 1. And after they all fail, it's 0. And they observed that most of them, whoops, came down to 0 here, it's 0. The failure was this, that a lot of them failed early, but some of them lasted longer. And these people were smart because they realized, they talked to some mathematicians, they fail in what's called an exponential failure pattern. And there is a distribution called the exponential distribution. It's a skewed distribution. The mean of that distribution is affected by the skewness. So the mean is somewhere here, let's say. But half of the bulbs failed earlier. The median is when half of them fail. And in skewed distributions, the mean is affected by the skewness, but the median is not. And so the median would be somewhere where 50% haven't failed is here, okay? And this is the median. And these people were smart, smarter than the public, Because when you buy light bulbs and you look at the label on the side, they say mean duration, 600 hours. Mean duration, 400 hours. When you go buy that light bulb, you look for that mean duration and you buy the one that has the longer one. But when you use it at home, you invariably say, oh, stupid light bulb, it failed earlier than those. Because that's what's happening. They know this. And that's the failure distribution of most things, not only of products, it's of humans. We die this way. A lot of people die young, but some people last long. We fail at this rate. Who knows this? Insurance companies. Insurance companies know that a lot of people fail earlier. And who are those people? Usually the young males because they do stupid things, or the smokers, or the alcohol drinkers, or the this or the that. And they call it life insurance, but they're not insuring your life, they're insuring your death. And they construct life tables, which are actually death tables. The death tables are, given that you are alive today and you are 43 years old, what is the chance that you will die before you're 44? Because if you're 43 and you're going to die in this period, I'm going to charge you a higher premium because I don't want to pay. I'm in the business of making money. I'm not in the business of protecting anybody's life. But if your risk of dying in the next year, that short interval, is low, I may charge you less. So they calculate these probabilities of dying. We call those conditional instantaneous probability of dying. And so conditional on what? Conditional that you were alive at the beginning, instantaneous because it's in that short period of 1 year. That's instant for them. And of dying, okay? That is actually called hazard. It's a probability of dying, but it's a conditional probability of dying in the next instant, conditional that you haven't died before. So when we talk about a composite time, the hazard of a composite, now we're saying, what is that hazard at this time point for that composite occurring, given that you have not had any component of that composite happen, that you will have a heart failure hospitalization or a heart attack or a stroke or a death in the next instant of time. And that instant usually for us is microseconds or whatever. But no, we don't do it that closely. That's how we measure it on days maybe. But that's the concept of time to event analysis. People that do manufacturing know this. People that do life insurance know this. You that are clinical investigators need to know this because this is what you're analyzing when you're looking at time to event outcomes, okay? They also, in fact, the first textbooks that came out on this, Kalpfeis and Prentice, they called the textbook failure time analysis or failure time distributions. Then they became smart, just like life insurance people, and called it survival analysis. Because nobody likes to talk about death, nobody likes to talk about failure, but it is time to event analysis. And so that's what it is, okay? Questions, comments on that? We're going to go through the mathematics of it, but I wanted to introduce the notion. Where does it come from? It's because things, including humans, fail following the skewed, not exactly exponential, but most of the times it is approximately exponential. Just like the bell-shaped distribution, which we call the normal distribution, nothing is normally distributed or bell-shaped, but it's approximately like that. And in large samples, means are approximately bell-shaped. Why do we call it normal? It actually was due to Gauss, a German mathematician in the 1700s. But Fisher, the father of modern statistics, was working with means of yield of barley and oats, things that are used for making beer in the UK. And he normally found that the bell-shaped distribution fit his data. And so he normally found it. He called it normal distribution, but it's not normal of anything, right? So most things may approximately fit the normal. Most things will also, most failure things, most time to event things will follow most of the time an exponential. But just like the bell-shaped distribution doesn't fit everything, we have the T distribution, we have the Cauchy distribution, we have other distributions that are symmetric that we can use. We also have the Weibull distribution, the Gompertz distribution, that are other distributions that fit the failure of things. We commonly use the normal, we commonly use the exponential. Why? They're very simple mathematically. They have beautiful mathematical properties. And so they approximately work. We do the simple things. If you want to complicate your life, yes, you can always do more complex things. But if you look at the literature, most of the literature does simple things. Why? So that people can understand what there is. Okay? All right, so I'm assuming, so then what happens is the test for the survival type of data is log rank test or the Cox model, and we'll talk about these. I'm assuming that all of you know what the t-test is. I'm not going to go into that. I'm assuming all of you know what Fisher's exact test is, or the chi-square test, because you all have had simple courses on statistics. I'm not going to go into that. But I'll talk about survival because that's what we more commonly do and what most people do not have a good understanding of how to analyze time to event data and what the hazard is. So, but before we get there, typical stages of analysis. At the end of the study, you will compare groups at baseline to make sure that randomization sort of worked, that the groups are comparable at baseline. That's what they call the famous table 1 of every clinical trial that's reported. Then you should, many people don't, but you should make sure that you did a good study, that the people came to visits, people took medication, that the staff actually provided the patient care that was supposed to be part of the protocol, that the data are good quality, etc. Then, after you assure yourself that I did a good study, that doesn't go in a paper, that's just internal consumption. You then do descriptive analysis. You want to understand your data. You do summary statistics, you should do plots. Plots will help you understand what happened. Then you do the inferential analysis of your primary outcome. This is when you answer the question of the study, and then you can rule out biases, put in context at the end of your paper, and then and only then you do descriptive and supportive analysis of secondary outcomes, subgroups, covariate adjusted. These are all secondary, supplementary analysis. We'll talk about those, but the analysis is this one. It's that crude one. It's not the descriptive stuff. It's not table 1. It's not these things. It is just that. And that is simple t-test, simple Fisher's exact test, simple log rank test. Nothing exciting. The statistician is bored doing this. Anybody can do it in 2 microseconds. If the data are clean, if everything is done properly before, then that's okay. But if the data are not clean, you have missing data, you have that, you have this and that, you still do the simple analysis, and now you have to try to do other things to make sure that you got a good result. Yes?
So what comprises the second one?
That means you look at what happened. Process outcomes or process variables are things of how you conducted the study. So you had, for example, people had to come to clinic visits at every 2 months. Well, what proportion of people did this? You also had you were going to take measurements of systolic blood pressure, of BMI, of this and that. Oh no, but I have missing data on this. Why did people not get me this covariate? Why I didn't get BMIs on this? I was supposed to do the lab, get results from the lab on this, but wait a second, I'm missing so many of these labs from this site or from this person. What is going on? So all of these things about conduct of the study that are in your protocol, they were supposed to have been followed. Things that were not followed, you want to know about. And that's just for you to know, I think we did a good study, but nobody mentions this in any paper because nobody shows their dirty laundry. It's always hidden. Yeah. So that's a good point. There is an argument for if you do a very large trial, it has to be simple because you cannot do a good large trial that's complex, measuring a bunch of things. It's also, some people say it's unethical to have the patient burden of collecting a bunch of stuff because a colleague of yours said, oh, why don't you collect echocardiograms too? Why don't you do this? Why don't you do a 6-minute walk test? Why don't you do this? Because that would be good information later. But it's not part of your research question. It is just the waste of your time and energy, but also of the patient's burden. And it's collecting a lot of things. Now, some people argue, I will do some follow-up to maintain the patient's interest in participating in the study if it's a long duration study. If I have the diet study, it's going to be 2 years. Well, if it's 2 years, I'm not going to just randomize them, tell them the advice, and then at 24 months, hope that they will come back, etc. I need to get patient rapport, do this with them. We had a study that same study of coronary primary prevention. This was all in men, and they had classes for their spouse, for their wives to learn how to cook low cholesterol diets that were healthy and tasty, etc. That's not anything to do with the study. It has everything to do with patient retention. So you can do all this stuff for patient retention, time, energy, money, whatever, because you don't want to lose somebody, right? So that's the kind of stuff that you do. But you have to worry about patient burden. That well, you send them a little birthday card, you send them a a Independence Day card, whatever you want to do. People do all sorts of stuff.
Our experience in only give me these trials, that usually the outcome is the EGFR decline, a certain amount of decline, like 50% decline, of they make some proposed outcome. They follow the patient for the EGFR measurement. They use the serum creatinine and then there are some values. The exposure they give, when the always get adjust, they keep on recording them time to time, thinking that they will be using analysis, but then they define the estimate framework. They just drop it.
Yeah, that's just a waste of energy and resources. And so they have to think, and pharma does this a lot because they have the money to do it. And they pay people for all of this stuff. But if you are an academician doing it, you have to seriously think it's whether it's worthwhile if I'm not going to use it.
And even during the COVID adjustment,
Mhm.
just adjust the baseline value.
Right.
They don't adjust for the time range, whatever.
Because it's the modeling of that is more difficult. That's why they don't do it. Yeah, but yeah, I mean, so if you collect it, you should use it. So you should plan to have a your measurement, the things that you do, be the necessary things. You don't have to just do everything. And so that is a huge problem in most trials. They don't do them simple. They complicate things because, oh, we may use this. Wow. Don't know. Okay. So how do we compare two groups? Usually that's what we're doing, control versus intervention. Well, For continuous outcome variables, we will do either, we have chosen one of these aspects. Most of the time it's the mean, but we could choose other aspects of that continuous distribution to look at. But we tend to just look at the central tendency, and we tend to do things on the mean. Why? Because the means will behave as a normal distribution, bell-shaped distribution, and the mathematics of that are easier. And we are usually taught that statistics is always looking at the mean. Well, that's wrong. That is a convenient thing to look at. We should always look at what we think is important to look at, how skewed it is, or how peaked it is, or what is the variance, or whatever. But we tend to always want central tendency. And we test it, as I said, t-test, or we could do it with standard non-parametric tests. In a table or graphically, this is a study on pain and acetaminophen, and looking at pain score. They had measurements at baseline. They had very few patients. They had 70 patients in the acupuncture group. They had 65 patients in the placebo group, and they were looking at pain, how it changed over time. But they presented it in the table at different weeks, from week 1 to week 56. They presented it in a graph descriptively. And then they chose, I didn't look at their protocol because back in those days, this was not registered. This was in 2004. And they chose to report at week 5, we had a significant difference. They should have said in the protocol, which is their outcome at which time point, but they tend not to do that. If we have when we have measurements, we have to worry about if I don't observe the outcome, we have missing data. We should try not to have it. We should not be more than a small percent. What is tolerable depends on whatever area you're working on. Most people, it's less than 1%, less than 0.5%. Sometimes it's almost 0%. And you can make up the missing data. That is not ever looked at nicely because you're making up the outcome. You may call it a fancy term like imputation, but imputation is making up data. That's exactly what it is by definition. We have, before you make up data, you need to find out if the reason it's missing, or we call it the missingness mechanism, if it's an informative one, it's missing not at random, so it's biasing your results. So you have to calculate the bias, adjust for the bias. That's very problematic. If it's missing randomly, that's okay, not bad. You want it to be missing completely at random. And what's the difference? At random means that it doesn't depend on the value. So for example, if you're doing a study on obesity or neurodevelopmental is your outcome, people that, parents may not bring their child for measurement if they know that there is a neurodevelopmental problem because of embarrassment or whatever. So if it's missing, you better make sure that, first of all, that it's not missing. But if it's missing, you try to, well, you actually, if parents miss the visit, you chase them and make sure that you get that child to do it. Because, or you find out why it was missing. Oh, because they were actually on holiday. They were somewhere else outside of the station that week where they were supposed to come. Okay. So then it's missing at random. It's not missing because the child was neurodevelopmentally compromised or something. So this is the kind of stuff that you worry about when you're missing the outcome. Now, completely at random means that, see, maybe the people on which it's missing is because it's those people that had the 24-month measurement during April and May. And the people it's missing are the rich people that could afford to go on holiday out of station. And the poor people or not so rich people stayed. And so the ones that are missing are not because of the neurodevelopmental status of the child, but it's related to the level of socioeconomic level of the parents. So it's related to some variable. So that's missing at random, but not completely at random. Completely at random is it's not related to anything.
At what point in time you got this information after the blinded data review or after doing the analysis? Because the assumption has to be taken care of in the stats analysis plan.
Right. So you have to specify how you're going to deal with missing data in your statistical analysis plan if you expect it. So
But I can't have this information in the starting of the trial.
no, but you'll say, I will examine the missingness mechanism. I will look at, I'll chase them down first. I'll make sure that I don't have missing. And if it's um, missing for whatever reason, I will find the reason it's missing and assess whether it's at random or that, and so forth. But in studies of obesity, for example, it's usually people that don't lose weight are the ones that don't get measured. They will not measure themselves because they feel embarrassed. So that is a problem. So many times we don't see studies where missingness can occur on the outcome. So you don't see a lot of things where it's measurements of things, unless you are able to make sure that the people, you will get them. So when you're doing this, you strongly advise you find out where that family lives. You get their WhatsApp number of them, of their relatives, of their job, of this, of their temple they go to. You chase them. You don't want that to be missing. That's the lack of missingness. I mean, missingness is a problem. And if you have more than one, if you have one or two out of 1,000 people, it's not a problem. If you have one or two out of 50 people, it's a problem. Because those two missing, you will have to do a sensitivity analysis if they got a benefit or worst case, best case scenario, and it will flip your result. So one or two is not good, depending on the sample size as well. So it's a tough thing. So I will show you that's why people tend to not do continuous outcome measurements as their primary outcome, unless they have to. And if they do, they chase people.
What we define in our current practices, we find that we have this much percentage of missing data, we will be doing these many sensitivity analysis for missing. Whether we specify the control multiple repetition or typical. But this thing that which people live this is the association of the missing data and some characteristics. How could I get this information prior to the
Well, so you have to think about possibilities of why would things miss? Why would people not would come? In obesity studies, we had this one trial, and it was people that worked at a university. There was intervention was given them on their computer, desktop computer, when they came every day. It would give them tailored messages on, for losing weight, and they had a way to measure themselves. And we found out that the secretarial staff would be not measuring themselves because they only had 30 minutes for lunch, while the higher administrative staff had 1 hour for lunch, so they had time to go and measure themselves. So it was based on their job. So you just find this out, and if you have too much of it, it may bias your result. That's what we're thinking. But we need to go on. There's so much topics to talk about this. So I'll stop you there. Okay. So what people do is tend to not have the missing, right? So categorical variables, we already talked about. You do Fisher's exact test. What many people do when they have multiple categories like none, mild, moderate, severe, they will score the categories and give 0 to none. Mild, they'll give a 1. They'll give maybe a 3 or a 2 to moderate, or maybe a 4. And severe, they may give a 9 or a 10. And then they construct a score and compare the scores. They could compare the frequency distributions, or they can do a mean scored test. And as I commented yesterday, whenever you're scoring something, you're opening yourself to somebody criticizing Why did you give a 3 to that? Why did you not give a 4 to that, etc.? So be careful unless it's a validated scoring mechanism. Binary outcome variables are the most common ones. And then there is no issue of scoring anything. It's a 0, 1. And we're interested in comparing the frequencies or usually the proportions, as we mentioned already. And we do it with Fisher's or the chi-square test if you want to get an approximate p-value. But in time to event analysis, what do we do? So I wanted to talk a little bit about survival analysis and where it comes from. So what happens in a typical clinical trial is patients come in, there's 5 patients. They're coming in at different time points. These 2 came at the beginning. This one came here, this one came here, this one came here. And suppose you were going to do baseline assessment. You have analysis at 5 months, and another assessment at, not analysis, sorry. You're assessing the developmental score at 5 months and at 12 months. So you're measuring these things. And let's say you stop recruitment at this point and you're going to analyze at this point. Well, some people you will have observed the outcome at that point, but some people, when you are doing the analysis, this person did not get the outcome during their 12 months of follow-up. This one did not. And this one, you did not wait for the 12 months because this person came in late. You only had less amount of time that they were exposed while the study was going on. So we want to study the time to the occurrence of the outcome. In this group, this person, it occurred early, and this person, it occurred late. And some of these will be randomized to intervention, some of them will be to control. And so we want to compare the incidence in rate in one compared to the incidence rate in the other. But we look at the time to that, so incidence is when it occurs, and incidence rate is time to that. But in some cases, the time is censored. And if I did an analysis here, an interim analysis here, it would be censored for multiple people, for this one, this one, this one, and this one. So depending on when you do the analysis, you will have had enough observation or not to the occurrence of the event. We call that censored information, or the data is censored because you're not able to observe it. And how do you deal with the censored data? So yeah, when you have it available at 12 months, you had it on B and D, but if outcome is a measurement, what can we do? If an event, what we do is we look at the censored information. So here's an old real data from an old study that would be unethical to do today. It was in 1963. These were people with leukemia, and they had been treated. They were in remission, and at that time, it was not known, should we continue doing some chemotherapy while they're in remission or not do anything? And so this was a study published in the journal Blood in 1963. There were 42 participants, 21 per arm. And the standard of care was not to do anything. And these people said, no, we should probably continue to give some sort of chemotherapy. So that was the new group. And these are the months at which time a patient relapsed. So in the standard of care, they're not getting anything. 2 people relapse after 1 month. 2 people relapse after 2 months, etc. And everybody, all 21, had relapsed by 23 months. Everybody relapsed. In the new one, there were 3 people that relapsed at 6 months. This person has a little plus sign, means that at 6 months, that person was censored, that they came in late, and I only observed them for 6 months, and they had not relapsed at 6 months. And so I know that we relapse sometime, but it's beyond 6 months. I don't know when. And then this one relapsed at 7. These 2 came in with 9 months to go or 10 months to go, where there were loss to follow up. And so you see that people here are, they went for 3 years, and some people, no one relapsed after 23 months. These people never relapsed. This one came in within 1 month of the study, and after 35 months had not relapsed. Okay. So then how do I find the average time to relapse? I can calculate the average time to relapse in this group by just adding them up and dividing. But in the other group where I have censored, what do I use? And this is the question that was solved by Kaplan and Meyer. Kaplan and Meyer were actuaries. Actuaries are the people that work in life insurance companies. They're the statisticians that calculate your probabilities of dying in the next year and how much we're going to charge you. So these people bring their information from working in life insurance and apply it to this situation here. And what they suggested is you have what you're observing is one of two time points, either the time from entry to the event occurring or time from entry to end the follow-up of that person. So when they were censored. So either you, for every person, you observe one of two time points, either the event occurred or they were censored at that point. And then they said, that's the outcome variable. I will now calculate that theoretical survival curve or estimate the survival curve. And what is the survival curve? The survival curve is the probability of not failing at a given time point t. That's exactly what this is. This is the theoretical survival curve of light bulbs. And this is, it would be at time t, so I say here at 320 hours, what is the probability of not failing? And I'll go back here and I'll say, oh, it is whatever it is here, 42%. So that's exactly what it is. So I calculate, I want to estimate the theoretical survival curve. We assume that we start at 1 and go down to 0, just like we did here, go down to 0. Everybody will fail. All those light bulbs failed. But, oh, here, not all the light bulbs are going to fail. Not all of the people are going to relapse. And so I'll have group A will be theoretically failing at this rate. Group B will be failing at this rate. And I want to estimate those things. But those of you that took calculus will remember that if I have a smooth function, I can calculate the tangent to that function. And that tangent is the first derivative. Nobody took calculus here. It's the first derivative is the tangent. And that's the tangent. You can see here, if I put the tangent here, this is less steep than this one. So at this time point, this is failing at a steeper rate than that. That tangent is related to the hazard. The life insurance people had a great name for this. We call it hazard. I don't know who came up with that term, hazard. But the life insurance people, you know what they call it? The force of mortality. It's a great name. The mortality is pushing down on you, trying to kill you. And it's trying to kill you faster here than here. If you survive, the force of mortality is less because it's flatter here, okay? And so that's, you want to calculate that force of mortality or that hazard at that time. Now, mathematically, that's the hazard rate ratio will be calculating the hazard rate here, the hazard rate here, and then taking the ratio, simple dividing one by the other, okay? But it's at time point 1, we'll have a hazard rate ratio. We'll have a hazard rate ratio at time point 2. And so I would have to report multiple hazard rate ratios. Hazard is usually with a lambda, another Greek letter, so you hire us. And that's usually the terminology we use, lambda. But people did not like having to report, oh, the hazard rate ratio at this time is this, at this time is that, at this time is that, etc. It would be nice if we had only one. You have only one if the failure distributions are exponential or if they are proportional. That's where the beauty of proportional hazards came. Because if the hazards are proportional, that means that the hazard rate ratio here is the same as the hazard rate ratio here. Now, we cannot visualize when it's in survival. We can visualize it when we look at hazards. But the hazard rate function is that it's lambda at a given time point, and it's the probability of surviving at time point t, surviving the next small interval of time, delta t. So this was surviving in life tables, that delta t was a year. And we are doing it, theoretically, it's an instant there, right? And that's the first derivative. And so we can look at the hazard rate function. We can get the cumulative hazard function. Why is it not showing? Oh. The cumulative hazard is just the integral of the hazard rate function. And the survival curve, don't worry about the formulas if you're scared of formulas. But the survival curve is basically taking the exponential function, exponential come into play, with the cumulative hazard function. The point here of showing you these formulas is not to scare you. It's to show you that if you tell me what the hazard function is, I can get the survival function. If you tell me what the survival function is, I can get the hazard function. And so when we're modeling and studying survival, we're actually using modeling hazards. Why? Because if I model the hazard and understand what affects the hazard, I can always go to the survival. And mathematically, it is easier to do manipulations on the hazard. That is why we study hazards, okay? And so we can estimate, if we don't have censored observations, the estimation of the survival curve is just the empirical cumulative distribution function. But what Kaplan-Meier suggested was, in their famous paper in 1958, how to do that estimate with censored observations. Don't worry about the formula. Nobody does it by hand anymore. It's all on the computer. But believe it or not, the most cited biomedical article of all times still continues to be this 1958 paper of the Journal of the American Statistical Association. Anyway, we can calculate that. This is what it looks like. This is a Stata did it for me. And what do we have? That the survival function is how many people have not failed yet in the different groups. And I can look at it this way, or I can look at it this way. So I can say, oh, how long does it take for half of the people to relapse? Or how many people still are in remission? In the placebo group, which is the red one, by about 8 months, half of them are gone into relapse. But in the other one, they lasted about 2 years. So if my grandma had leukemia, I would want her to be in the intervention arm. Or I could go the other way and say, at 1 year, how many have not relapsed? I go up, and here we have about 30% in one arm, but here it's about 75%. I can go the other way, whichever way I want to go and interpret. But this is now what people present, the Kaplan-Meier estimates of the survival curves. So they're estimate survival curves. But nobody is just satisfied with showing graphs. People love p-values. How do I compare the graphs? Well, I could compare them at a given time point but we observe that this is a step function. And the steps only occur when somebody fails in one group. So there's only a few places where the curves can be different. Because if I compare at time point 18 months, I get that difference. At a time point 18.5 months, I get the same. At 19, I get the same. At 20, I get the same. Until somebody fails at 21, then things change. So I look at all the possible different failure times, and I compare the curves at a given time point. And I only have a few time points to compare them. And so for every time point I'm comparing, I have m different failure times, little m. And for each one, I'll construct the 2x2 table, because that's how many people are at risk in one arm and the other, and how many fail in one arm and the other. So now I can construct m little 2x2 tables. And we want to combine those m 2x2 tables. And this is what Mantel Hensel in the United States proposed, was exactly the same thing as Richard Peto and his brother, I forget his first name, proposed in the UK. So you will see this called either the Mantel Hensel log rank, or you'll hear it called the Peto log rank, or the Peto log rank, or the Mantel Hensel Peto log rank, or more commonly, the log rank. Nobody attributes it to them. It's a way of combining those 2x2 tables to get one single 2x2 table. We're not going to go through the mathematics of it, but it's simple here. And later, people showed that the log rank statistic is nothing but a generalization of Wilcoxon's test. Okay, so famous Wilcoxon was an American statistician during World War II. So one can see that the log rank test is taken, it's based on a chi-squared statistic, and the chi-square statistic is looking at, like all chi-square statistics, the observed events minus the expected events at a given time point in a given 2x2 table, but you can weight it differently to get different types of tests. If you weight of 1, you get the log rank test. If you weight it by other different things that have been proposed, you get different tests. Now you say, well, why do you do this? Well, look at the weights. What the log rank test is doing is comparing all of the different points and giving them equal weight. But what is happening is, if you go back here, at this point, I have 21 people and 21 people in both groups. By the time I'm here, when I'm observing the big differences, I have very few people left in the study. So therefore, I have more uncertainty around here. So I would want to give more weight where I have more certainty of the actual shape of the distribution than here. So, and here the survival is higher and the sample size is higher. So different people have proposed that, and that's what this is, again, Peto in the UK, Guion in Texas in the United States proposed. Most people are unaware that you can. So if I'm doing a trial and my outcome, I'm going to see early effects. Should I not put in the protocol that I will use one of these weights, weighted log rank, because I want to emphasize and detect early effects? If I think that my study, the effects will be later as opposed to early, then I could choose, there are other weights that will look at giving more emphasis to later effects. Most people don't know that these things exist. Your statistician, I think, probably knows that these things exist. But unless people ask for it or they have a discussion with their statistician, most people don't even do this kind of stuff, right? But I just mention it so you know that these things do exist. So what is a statistical test for the primary hypothesis? Which one should I use? It depends on your outcome variable. So if it's continuous, you'll do a t-test. T-tests are asymptotically a z-test. I can do the Mann-Whitney. U, asymptotically, it's a z-test. If binary, Proportion of events are chi-squareds with 1 degree of freedom. Fisher's exact test is using the chi-squared with 1 degree of freedom. If it's time to event, the log rank is a chi-squared with 1 degree of freedom too. And those of you that are not statisticians, I will tell you that we know that the square root of the chi-squared with 1 degree of freedom is also a z-test. So when we talk about the analysis of a clinical trial, we always focus on that z statistic, because the z statistic is what all of these things are basically doing, one or the other, okay? Now, before we go, I don't know if you want to take the break. Yeah, we'll take a break now. This is a good time to take a break, because the next thing will be secondary analysis. But any questions about survival analysis?